In this lesson, we're going to look at the zeros of polynomials. We're going to make sure we understand what a rational number is. Then we're going to look at the rational zero theorem, and we're going to apply the rational zero theorem to find all possible rational zeros of polynomials. Then we'll use division to test to see if the zeros that we found are actually zeros of the polynomial. So this is kind of a doozy of a lesson. I'm ready and excited to get started. Let's go. Let's start off by discussing what rational numbers are, and let's make sure that we can classify rational numbers versus irrational numbers. So a rational number is a number that can be made by dividing two integers. So an integer is a number with no fractional part, either positive or negative. So any number that can be rewritten as a fraction with integer numerator and denominators, then those would be considered rational numbers. An irrational number is a number that cannot be expressed as a fraction for any integers, and it has a decimal expansion that neither terminates nor becomes periodic. So essentially, it's when you have a decimal number that does not have a repeated pattern within it and it does not end. So an example of an irrational number would be a number like pi. So when we start looking at these, we have 7/2, which is it's the same thing as 3.5, but it's written as a fraction. This is rational. Square root of 3 is irrational. Negative 3/4 is rational. 2 minus the square root of 5 is irrational. 6 is rational. If you think about it, 6 is the same thing as 6 divided by 1. It can be written as a fraction with two integers. If that's the way you're thinking about this. Also, you could just know that all whole numbers and all integers are rational numbers. That is also one way to think about it. Then we have the square root of 16. Well, the square root of 16 actually equals 4. So that is a rational number. So don't just think that because we have a square root in it, it has to be irrational. If it can be evaluated and you get an integer result, then that is a rational number. So we need to make sure that we know the difference between rational and irrational numbers because we have something called the rational zero theorem. So the rational theorem states that if a rational zero exists for a polynomial, then it must be of the form p divided by q, where p are your factors of a sub 0, which is your constant term in your polynomial, and q are the factors of a sub n, your leading coefficient. Recall from our previous lesson on the introduction to polynomials, polynomial is in general written in this form. So it's saying essentially that I take the factors of the constant term and I divide them by the factors of the leading coefficient, and that will give me a list of all of the possible rational zeros for a polynomial. So let's take a look at an example where we're going to list all the possible rational zeros of the polynomial f of x equals 4x to the third minus 13x squared minus 32x minus 12. So my a naught term is equal to negative 12. My a sub n term is equal to positive 4. So in my possible values for p, I'm going to have all the factors of negative 12. So that's going to be positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 4, positive or negative 6, and positive or negative 12. So these are all the possibilities for the numerator, because the numerator is created by the factors of the constant term. Now, our q values, our possible q values, are all going to be factors of 4. So my factors for 4 are positive or negative 1, positive and negative 2, and positive and negative 4. So what we do is we create the fractions kind of methodically from these values. Let me show you what I mean. We end up having positive or negative 1 over positive or negative 1, positive or negative 2 over positive and negative 1. So what I'm doing is I'm starting with all the possibilities from the numerator over this 1 starting off. Positive or negative 3 over positive and negative 1, positive or negative 4 over positive and negative 1, positive negative 6 over positive or negative 1, and positive or negative 12 over positive or negative 1. We're going to do that same process. I'm going to make all these ones in the denominator red just so you can see that that's where that 1 is coming from. We're going to do that same process for each of the different denominators. So we have positive or negative 1 over positive or negative 2. Positive or negative 2 over positive or negative 2. Positive or negative 3 over positive or negative 2. Positive or negative 4 over positive or negative 2. Positive or negative 6 over positive or negative 2. Positive or negative 12 over positive or negative 2. Then we're going to do the same thing with the last one. Again, I'm going to make those 2's red just so you know where I got them from. But now we're going to do the last. We're going to take all of the possible numerators and put them over positive or negative 4. So positive or negative 1 over positive or negative 4. Positive or negative 2 over positive or negative 4. Positive or negative 3 over positive or negative 4. Positive or negative 4 over positive or negative 4. Positive or negative 6 over positive or negative 4. And we have positive or negative 12 over positive or negative 4. So again, those 4's all came from the factors of that leading coefficient. Okay, so now we can simplify all of our fractions. What I'm going to do is I'm going to take each of these at once. Let me do this in a different color. Let's do purple. We're going to simplify each of these. Any number divided by 1 is equal to itself. And so we're going to end up with positive or negative 1 because I either get positive 1 over positive 1, which is positive 1, or positive 1 over negative 1, which is negative 1, or negative 1 over negative 1, which is positive, or negative 1 over positive 1, which is negative. So we end up with either a positive or negative 1 from this one right here. So same thing for each of these. So I'm going to get plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So that takes care of each of these. Now we have these in the second row. So something interesting is going to happen. We have plus or minus 1/2. I can pull the plus or minus out to the front because, again, we would either get a positive or negative answer. 2 divided by 2 is the same thing as 1. So we've already accounted for this one. It's the same as our very first one. So we don't have to write it twice. Okay, 2 divided by 2 is equal to positive or negative 2 divided by positive or negative 2 is equal to and the same as positive or negative 1 divided by positive or negative 1. So we don't have to write it twice. Then we have positive negative 3 over positive or negative 2. So we have 3/2, plus or minus 3/2. So we took care of that one and this one. Next we have 4 plus or minus 4 divided by plus or minus 2. That's going to be equal to 2, which we've already taken care of right here. So we don't have to write that one again. We've already accounted for it. 6 divided by 2 is equal to 3, which we've accounted for up here. So we don't have to write that one down again. And 12 divided by 2 is equal to 6, which we've accounted for right here already. So we don't have to write this one again. The last row we have 1/4, so plus or minus 1/4. Plus or minus, so we took care of that one. We have plus or minus 2 divided by plus or minus 4. When simplified down, 2/4 is the same thing as 1/2. We've already written this one, so I don't have to write it again. We have not written a 3/4, so we have plus or minus 3/4. Put that one down. Now I have 4 divided by 4, plus or minus 4 divided by plus or minus 4. That's the same thing as 1/1, so we don't have to write that one again. That one's already been accounted for. We have plus or minus 6 over plus or minus 4. Well, that's simplified down, that's equal to 3/2, which we've already accounted for right here. 3/2 and 6/4 are the same, so I don't have to write that one again. And we have plus or minus 12 divided by plus or minus 4. That equals 3. We already accounted for 3 up here, so I don't have to write that one again. So our possible rational zeros for this polynomial are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, plus or minus 1/2, plus or minus 3/2, plus or minus 1/4, and plus or minus 3/4. So this seems like a long task, but when we are looking at larger polynomial functions and we're trying to figure out how to factor them, knowing their possible zeros gives us a starting point to try and divide it out evenly to find the different factors until we can get it down to something that we can easily use like the quadratic formula on. Okay, so we're going to do the same thing. We're going to list all the possible zeros for g of x. Now, take a look at g of x, where it's written as g of x equals negative 6x plus 1 plus 8 to the times x to the third minus 7x to the second. So first off, we need to rewrite this in the correct order. So we would write it in descending order from the exponent. So that's going to be 8x to the third minus 7x squared minus 6x plus 1. So for my numerators, for my possible zeros, I have a positive 1, whose factors are plus or minus 1. For my denominator, I have 8, okay, which factors are 1, I'm going to write the plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So this one is a little bit simpler because my factors for my numerator, there's a lot less of them. There's a lot in the denominator, but there's only one, well, technically 2 factors for 1. So we just have to take that numerator, plus or minus 1, and put it over each of the factors in the denominator. Okay, so that's our first one. We've already taken care of the numerator with that denominator. So the next one would be plus or minus 1 over our next possible denominator, which is plus or minus 2. Then we have plus or minus 1 over our next denominator, which is going to be plus or minus 4. And then we have our possible numerators, plus or minus 1, over our last denominator, which is plus or minus 8. So 1 over 1 simplifies down to plus or minus 1. So again, I'm just kind of going through and cleaning this up a little bit. We've finished that one. Plus or minus 1 over plus or minus 2 is just plus or minus 1/2. That one's taken care of. Plus or minus 1 over plus or minus 4 is equal to plus or minus 1/4. Taking care of this one. And we have plus or minus 1 over plus or minus 8, which is the same thing as just plus or minus 1/8. And so these are all of our possible zeros for this function. So on this one, you had to be careful because the order of our polynomial was not written in descending order based on their exponents. And so we had needed to start off by rewriting that to make sure that we use the correct leading coefficient and the correct constant term. Okay, so in this next example, we're told the function below has at least one rational zero. Use this fact to find all zeros of the function. So we have our leading coefficient is a 1 and our constant term is a negative 20. So I'm going to write out the factors of negative 20. Those are all of our possible numerators. And then we're going to take our leading coefficient, which is a 1. If there's nothing written there, it's assumed to be a 1. So our possible denominators are plus or minus 1. We're going to list out all of our possible rational zeros, and then we're going to start picking them to find out which ones are actual zeros. Because our only value in the denominator that's possible is a 1, essentially we have all these numerators over plus or minus 1. When you divide by 1, it doesn't change the number. So our possible zeros are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. And so what we're going to do is we are going to take these, you can go in order, you don't have to go in order, but you do want to make sure that you're methodical in how you do this. We're going to divide each of these essentially by x minus c, where our c values are our values that are possible zeros. When we do that, we're checking to see, do I get a 0 remainder? If I end up getting a 0 remainder when I divide, then that means that that is a factor. So we could rewrite our factor as the factor we just found times what would remain in this case would be a quadratic, which we could then use the quadratic formula for. So this is super helpful in order for us to be able to find the zeros and then factor polynomials. So first one I'm going to do is 1, and I'm going to use synthetic division to divide. So I'm going to write down my coefficients for my polynomial, and we're going to synthetic divide. Here we go. Bring down that first coefficient. 1 times 1 is 1. I'm adding that column. 8 plus 1 equals 9. 1 times 9 is 9. 11 plus 9 is 20. 1 times 20 is 20. Negative 20 plus 20 equals 0. That means that 1 is a factor. Or I guess I should say 1 is a 0. It is so x minus 1 is a factor. So if x minus 1 is a factor, I could rewrite this polynomial up here as x minus 1 times the remaining polynomial, which would be x squared plus 9x plus 20. Now I could either factor this, or I could use the quadratic equation to figure out the factors of, or the zeros of this quadratic. So I'm going to go ahead and factor this because I can find two numbers that multiply to get 20 and add to get 9. And that's going to be x plus 4 and x plus 5. So my factors of this polynomial are x minus 1, x plus 4, and x plus 5. And so my zeros are going to be, we already found one of them, 1, negative 4, and negative 5. The way I would get negative 4 and negative 5 is I would take x plus 4 equals 0 and solve for x. You get x equals negative 4. And then you would do the same thing, x plus 5 equals 0. Solve for x, you end up getting x equals negative 5. So these are my zeros for this polynomial. Now notice there are 3 zeros. Notice the degree of that polynomial is a 3. So your zeros with their multiplicities have to add up to the highest degree of your polynomial. Just keep that in mind. That's a way that you can check yourself. But we have successfully found all the zeros of this function. I'm going to do another example. Again, in this case, we have our leading coefficient, which makes up our denominators, is an 8. Our constant term is 28. So I'm going to go ahead and pause and write out all the possible zeros. I'm going to suggest that you pause and also try on your own first, and then check your possible zeros with my list that I've written at the end. I'm going to just skip to the last part. I'm not going to write any duplicates, and I'm not going to write out the entire list with the duplicates in it. I'm going to ask that you do that on your own and then check your final list with mine. All right, so when we look at the list of possible zeros for this polynomial, we have quite a long list. We have plus or minus 1, positive or negative 1/2, positive or negative 1/4, positive or negative 1/8, positive or negative 2, positive or negative 4, positive or negative 7, positive or negative 7/2, positive or negative 7/4, positive or negative 7/8, positive or negative 14, and positive or negative 28. Now remember, I've simplified and removed all the duplicates. So when you first listed them out, you have a lot more, but there are a lot of duplicates that you can take out, and you just have to write each zero once. So, or each possible zero once. And so now what we're going to do is we're going to use some synthetic division. I'm going to go ahead and start with 1 and synthetic divide. 8, negative 42, positive 33, positive 28. So bring down that first coefficient. 1 times 8 equals 8. Add those together and we get what? That'd be negative 34 times 1 is negative 34. Add those together, you get negative 1. Negative 1 times 1 is negative 1. And 28 plus negative 1 is 27. My remainder is 27, so this is not a 0. I can try negative 1. Let's try negative 1. I'm going to do the same process. Bring down the 8. Negative 1 times 8 is negative 8. Negative 42 plus negative 8 is negative 50. Negative 1 times negative 50 is positive 50. And add those together. 33 plus 50 equals 83. Negative 1 times 83 is negative 83. That clearly is not going to get us to 0. That gives us negative 55 as a remainder, and so this one is not a 0 either. Okay, so based on that, you can keep checking. You would check 1/2. When you synthetic divide with 1/2, you get a remainder of 35. It's not going to work. Let's try negative 1/2. Don't freak out with the fractions, please. 8, negative 42, 33, 28. So I'll bring down that first one. Negative 1/2 times 8 is negative 4. Negative 42 plus negative 4 is negative 46. Negative 1/2 times negative 46 equals positive 23. 33 plus 23 equals 56. Negative 1/2 times 56 is equal to negative 28, and I get a remainder of 0 because 28 plus negative 28 is 0. So I know that negative 1/2 is a factor, so I'm going to put a big red check next to it. Then I know that I have x plus 1/2 because remember, it's x minus c. So if I have x minus negative 1/2, that's the same thing as x plus 1/2. So x plus 1/2 is a factor, which makes negative 1/2 a 0. But I can write out my remaining polynomial based on this information, and I get 8x squared minus 46x plus 56. I'm going to erase some of my previous work up here just so I have room because I don't want to do the AC method on this one. To find out the zeros for that quadratic part of this, I'm going to use the quadratic formula. So if you recall, and I'm going to do this in purple, and I'm going to put it in a big purple cloud, the quadratic formula tells us that to find zeros of a quadratic, you do x equals negative b plus or minus square root b squared minus 4ac all over 2a. So in this case, I'm going to have x equals negative 46, which is positive 46, plus or minus the square root of b squared, which is negative 46 squared, minus 4 times my a, which is 8, times my c, which is 56, all over 2 times 8. this equals, I'm going to start simplifying some of the things under the discriminant, which is that square root, and then multiply the bottom out. So you get 46 plus or minus the square root of 2,116 minus 1,792. That's a 9. I know it's really small. All divided by 16. So when I do 2,116 minus 1,792, I get 324. So this is going to be 46 plus or minus the square root of 324 all over 16. So 324, when you take the square root of that, we're going to cross our fingers and really hope it's something nice. It is. That equals 46 plus or minus the square root of, or not square root, we got rid of the square root. So it's just 46 plus or minus the square root of 324, which is equal to 18 all over 16. So now we're getting a lot nicer. I'm running out of space, but we're going to deal with it. We get 46 plus 18, which is 64 divided by. So I'm going to show this work down here to get these remaining zeros. I end up getting 46 plus 18 over 16, which equals 64 over 16, which equals 4. So 4 is a 0. And then we also have 46 minus 18, which is 28, divided by 16, which is equal to 7/4. So my zeros, this is complicated. My zeros for this polynomial, we have found to be -1/2. Then we found that with synthetic division. Then we rewrote our polynomial as its factors that remained. We used a quadratic formula on the quadratic portion of this. And we were able to find that the other zeros are +4 and 7/4. That's not something you could easily guess from picking from this list. Now, what you could also do is you could do synthetic division on each of the different options here until you got zeros for as remainders for 3 of them. That would not be very efficient since we do have the quadratic formula that you can use. Quadratic formula is super helpful on these topics. So please make sure you know how to synthetic divide. Please make sure that you know how to do the quadratic formula. I'm going to go ahead and stop this part of the video and we'll look at more examples and talk about irrational zeros and irrational roots when you watch part 2. Thank you.